power series 2, we will continue with the proof of the last theorem which you mentioned. It's the most basic result about power series. So let us get into that. So we have a power series which is summation Cn z minus a to the power n running from 0 to infinity, and Cn's are in C and a is also in C, right? Then what do you want to say? Then there exists a unique R such that R may be 0 or it may be infinity, so that 1 for all z in VAR, the series, the power series summation Cn z minus a to the power n is convergent, and 2, if mod z minus a is greater than R, the power series is not convergent. Okay, yeah. Notice that this R has to be unique. Okay, uniqueness is easy. Okay, suppose there are R1 and R2 with this property. Okay, then let's look at this. This is your Z, this may be your R, this may be your R1, this may be R2. Then I can find a Z in between, right? So that mod Z minus A is, okay, yes. What do I want? So R1 should be less than mod Z minus A less than R2. Okay, now there is a problem because remember R1 is what I chose. Okay, R1 is the R which we had. Okay, anyway, so now what did we have? It said that if mod Z minus A is greater than R1 and R1 has this property for mod, okay, for Z such that mod Z minus A is greater than R1, the series is not convergent. But on the other hand, since mod Z minus A is less than R2, R2 satisfy these two properties, the power series must be convergent. So these are contradictory, and hence we find that there is a unique R if it exists. Okay, now how do I find it? Okay, so R is unique. So pause, review, proceed. Now how to find it? Okay, that is again, you just have to think. Let us see, suppose I look at the property, it said that for Z is in VAR, the power series is convergent. If Z is outside this open ball, in fact it's outside the closed ball, because I want mod Z minus A must be greater than R, not greater than or equal to R. If it's greater than R, it's this power series is not convergent, it is divergent, right? So how do you think I can find R? So let us collect all Z in C so that, okay, the power series Cn Z minus A to the power n is convergent, right? In this, what we do is look at only this set mod Z so that Z is in C, and so that summation Cn Z minus A to the power n is convergent. Okay, now this set is not empty. Why? Because if we take Z equal to A, then this is convergent, right? When Z equal to A, this is C0 plus C1 0 plus C2 0, etc. That's convergent, because the C equals of partial sums is C0 C0 C0, right? Therefore it's convergent, right? Therefore this is non-empty, and hence this set is also non-empty. Okay, this is at least mod A. Okay, maybe I should say, sorry, mod Z minus A. I'm very sorry for that mistake. Mod Z minus A, so that Z is less than C. Okay, mod z minus a. Okay, right. Yeah. So 0, therefore 0 belong to this set. Is that clear? Very good. Now this is a subset of positive reals. Okay. Remember, this is always a real number. Therefore, it cannot be infinity or anything. It's just a positive real. And 0 belong to this. Therefore, what are the two possibilities? Either it is bounded above. So this set, call this set if you want. Okay, A. So A is a subset of this. So two cases, A is bounded above or A is not bounded above. Right? Suppose A is bounded above, since it's non-empty, I can let R to be the LUB of this set. Mod z minus a as such that summation Cn z minus a to the power n is convergent. This is just other than LUB of a. Yeah? Okay. Right? Call this R. Right. Now what do I know? So R satisfies. So if otherwise, suppose A is not bounded above. If A is not bounded above, we let R equal to infinity. This is just a symbol. What does that mean? That means for every complex number z, mod z minus a will be there. That is summation Cn. Are you following this? The subset A is not bounded above. Okay, right. Now what do I want to do? The first thing is notice that R satisfies. There are two conditions, right? It satisfies condition 2 automatically. Whatever be the R, whether R is finite or R is infinity, R satisfies. Why? Is that clear? Why? Because if mod z minus a is greater than R and if summation Cn z minus a to the power n is convergent, then mod z minus a belong to a, right? But R is the LUB. You understand? Yeah. This is in the case of when A is bounded above. If A is not bounded above, then there is no problem. Okay? Because what does it mean? You want to say mod z minus a is greater than infinity, then it has no meaning. Do you follow that? Therefore, R satisfies condition 2. So just pause, review, and proceed. So we found R. Okay. Now what is it we want to prove about R? Remember, we want to say something more. So, okay, you fix any z in BAR. Then what am I supposed to show? I am supposed to show Cn z minus a to the power n is convergent. Okay, this is not obvious. Remember that. Why? You see that how did you construct the set? This is a okay. For example, suppose let us say R is, just make sure that you understand. I'm just trying to give some example. I have to find where my cursor is. Yeah. Yeah. So suppose my R equal to 3. Alright. And if you take a z such that z minus a equal to 2, I do not know whether Cn z minus a to the power n is convergent. You do not know. You understand? Because for the reason there might have been some other z naught, so that z naught minus a equal to pi by 2, and this series Cn z naught minus a to the power n is convergent. Therefore, pi by 2 appears in the set A. Are you following? So, just because mod z minus a is less than r, we cannot conclude the corresponding power series is convergent. Keep that in mind. So, this is how you have to analyze the proofs slowly. Okay, right. So, how I have to argue carefully. So, how do I do that? So, let us start with the z in VAR. Then what do I know? Mod z minus a is less than r, right? So I have 0 mod z minus a. This may be my r may be positive, but choose an r so that mod z minus a is less than r, less than capital R. Right? Now what do I know? This r is the LUB of a, and little r therefore is not an upper bound. So that means there exists a z naught in VAR, right? Or simply say, so that what happens? R is less than mod z naught minus a, and that's less than r, right? If remember, r is not in upper bound of a, that means there exists some there's an element here which is, okay, there is an element here some z naught in C, so then mod z naught minus C is greater than r. Is that clear? Okay, good. So what do I know? Therefore I know Cn z naught minus a to the power n is convergent, right? And if the infinite series is convergent, the sequence of the terms, namely z naught minus a to the power n, this sequence is convergent to 0, right? Remember this, I already said that summation an is convergent implies limit an is 0. That means look at the sequence an, this is a convergent sequence, and where does it converge? It has to converge to 0, right? This is convergent, right? Keep that in mind. Now let's go back to what I want. What I want to show is summation Cn z minus a to the power n is convergent. This is what I want to show. But what I know is Cn z naught minus a to the power n is convergent, right? So, and also I know z minus a is less than r, that is less than mod z naught minus a, that's less than r. Keep all these things in mind, right? So what is that I plan to do? I plan to use this somehow. So what I will write is Cm z minus a to the power n, I will write as Cm z minus a to the power n by z naught minus a to the power n into z naught minus a to the power n. Can I do that? Yeah, right? Very good. Remember, if I had gone through my infinite series lectures, I would say the most important thing is comparison test and comparison with geometric series. Okay, so can you see there is a geometric series somewhere here? Yeah, good. So I am going to show this series is absolutely convergent. Okay, claim this is absolutely convergent. Okay, so I have to estimate this. So mod Cn mod z minus a to the power n equal to mod Cn minus mod z minus a by z dot a minus n into mod z dot minus a to the power n. Yeah, okay. Is all right? Very good. Now let us look at this. So let me call this as a row mod z minus a by mod z naught minus a. Now let's look at it. Mod z minus a is less than r, that is less than z naught minus a, therefore rho is less than 1. Therefore what do I have? I have this is less than or equal to, okay, mod cn and z naught minus a to the power n and rho power n. Okay, this is rho, right? Okay, so now rho is less than 1. This is, so if I simply have rho n, it will be convergent. Therefore what do you think I should do? This is almost like a geometric series, except I have no idea about this. So is there any brainwave? How to deal with this? Yes, let's go back. We saw this is convergent. What did we see? We saw this fellow is convergent to 0. In particular, it is convergent. That's good enough for me. If it is convergent, if an is a convergent series, then an is bounded sequence. Right? Sorry, if an sequence an is a bounded sequence, then mod an is less than or equal to m for all n. There exists some m. Right? So in particular, therefore, there exists m such that mod cn and mod z naught minus a to the power n is less than or equal to m for all n. Why? Because this sequence is convergent. Yeah? Okay. So what do you think I have got? So I have got that my summation cn z minus a to the power n in modulus is less than or equal to summation m into rho power n. And where rho is less than 1. Therefore this is convergent. This is convergent. Therefore by comparison to this is convergent. That means the series Cn mod z minus a to the power n is absolutely convergent. So pause, review, proceed. Okay. Now let's sit back and go through the proof. Okay. What have we achieved? What have we achieved? Okay. See that we had actually shown this series. Okay, think of this as a series of functions. Okay, f1 of z, as usual, f1 of z is cn z minus a to the power n. Then what I have shown is f1 of z, okay, for z in bar, okay, is less than or equal to m into rho power n. Call this as mn, right? Therefore, what do I have? I can use Weierstrass test. Okay, that shows summation f1 of z is uniformly and absolutely convergent. Where? For all z in bar. Okay, this is true for every z in bar. Right? Therefore, by Weierstrass test, I know that series is uniformly and absolutely convergent. So, let us summarize. If 0 less than or less than capital R, then the series summation Cn z minus a to the power n is absolutely and uniformly convergent in BAR. Okay, right? So, and what have we shown that? We have shown there. This is a summary, but what we did it, we start with the Z in BA capital R, and in purchase, therefore choose an R, so that mod Z minus A is less than R, and that is less than capital R. You understand? Therefore, in particular, for every Z here, Cn Z minus A to the power n is convergent. In fact, we have shown it's absolutely convergent. And where does it uniformly converge? It uniformly converges in the smaller disk BA, small r, little r. Okay. Now make sure these are the points which students miss while reading. Okay. So have you proved that for our R satisfies 1? Condition 1. What is the condition 1 said? It said for every Z in BA capital R, the series Cn Z minus A to the power n is convergent. And for every Z such that mod Z minus A is greater than R, this is 2. Summation Cn Z minus A to the power n is divergent. Okay. Why this is divergent? We had already seen that. Why? Because if mod Z minus A is greater than R, then mod Z minus A is greater than 0. Right? Okay. Do you follow that? Yeah. No, sorry. This is by definition. I'm sorry, I take back. And this is divergent. This already proved too. Okay. So have you proved the theorem? Go back. What did you do? Given as a power series, okay, like this, there is a unique R such that R it satisfies condition 1, it satisfies condition 2. And uniqueness we already established earlier. Okay. And we also said that such as this R satisfies condition 2 automatically. Okay. So now the main point was we wanted to prove R satisfies condition 1, but what did we actually prove? We proved that if little r is less than capital R, on the smaller disk BA little r, the power series is uniformly convergent. Right? Okay. Therefore, what is the outcome now? The outcome, therefore, is since Cn Z minus A to the power n is continuous on C and hence it continues on BAR, right? You understand? And hence it is continuous on BA small r, 0 less than r small r. So, what I have shown is this series, this sequence Cn Z minus A to the power n, call this the Fn of Z. These are continuous on BA small r. And this series is uniformly convergent on BA small r. And you know the uniform limit of a sequence of continuous functions is continuous, therefore this is continuous. Therefore, if I define f of z to be equal to Cn Z minus A to the power n 0 to infinity, okay, for Z in BAR, then f of is continuous on BAR. Yeah, but I say this actually proves f is continuous on BA capital R. Why? Because start with any Z in BA capital R, as we did earlier, there is an R such that, okay, Z belong to BA little r, and on which the function is continuous. Therefore, f is continuous at Z. Therefore, f is continuous on each and every Z in the larger disk BA capital R. Therefore, what have we shown? So, we are also shown the power series of Z which we define. This defines a function z minus a to the power n 0 to infinity for every z in the disk Br. Okay, and this is continuous function. This is what we have proved. Okay, right? And also we showed that this series Cn z minus a to the power n 0 to infinity is uniformly convergent on every VAR where 0 less than or less than capital R. So the natural question you might ask whether this is uniformly convergent. So question. So pause, review, proceed. Question to ask is, let me just give, this R is called the radius of convergence of the power series. And VAR is called the disk of convergence. Right? Remember, if R is infinity, then this is all of C. Yeah? Keep that in mind. Okay. Now the question we have proved that was, if this is something like VAR, suppose this is my A and this is my VAR. So what I showed this, on any smaller subdisk, this is convertible. This is small r, that is capital R. So on this BR, this is convergent, uniformly convergent. Now you can ask whether this is uniformly convergent on BA capital R. Okay, this is a question. The answer is no. In fact, it's never. But let us look at the simplest case, z power n 0 to infinity. We know the radius of convergence for this is 1. This is a geometric series, we know that. Right? Now suppose this is uniformly convergent. Okay, and where does it converge to? It converges to 1 by 1 minus z. That also we know, right? Because the partial sums are 1 minus z power n by 1 minus z, and since mod z is less than 1, okay, this is 1 by 1 minus z by z power n plus 1 by 1 minus z. This goes to 0, therefore this whole thing goes to 1 by 1 minus z. Okay, therefore this is a function. And if it is uniformly convergent, then what should happen? Yeah, so I want to say this is not uniform convergent. Suppose uniform convergent, then that means there is an epsilon. Okay, for every epsilon greater than 0, there is an m, so that for every z in V01, what should I have? The partial sum is Sn z minus 1 by 1 minus z. Okay, that should be less than epsilon whenever n is greater than or equal to capital N. So that for all n greater than or equal to capital N, if you want like that, this is what I have to have. But what is this? This is 1 plus z power n by 1 by 1 minus z. That should be less than epsilon. Yeah, right. Now do you see a problem here? This you had already seen this. Why this is a problem? Multiply this 1 by 1 minus z, then what will I have? I'll have 1, will have, minus z will be this. So 1 minus z into 1 plus z power n by minus 1 by 1 minus z. This should be less than epsilon. This should be true for all z in mod z less than 1. So that mod z less than 1. Yeah, but what is this? This will give me only something like z power m plus 1 by 1 minus z. Yeah, because 1 will have minus z, this will cancel, minus z power n plus 1, therefore it's a minus, that minus I can imagine. This should be less than epsilon. Okay, this should be true for all z, so that mod z is less than 1. Right? And this is a problem. Why? Why can't I have that? This leads to a contradiction. This is not true. Cannot happen. Why? If you have gone through my uniform convergence lectures, this is very easy for you to do that. Yeah? Will you do that? Yeah. Let me see. Let me hope that you do that. Okay. So what I have shown is, so this is, please remember, therefore, if R is the radius of convergence, so check radius of convergence, then the power series summation Cn z minus a to the power n is uniformly and absolutely convergent on BA or for any R, little r less than capital R. Okay, but it may not be uniformly convergent on the entire disk. Okay, so if I define f of z to be Cn z minus a to the power n 0 to infinity for z in BAR, by f of z, by it is nothing other than the sum of the series. Okay, then f is a continuous function on BAR. Okay, this is a byproduct of the proof. Okay, the next thing I would like to show is that it is it's a differentiable. Okay, now f is a function from where to where? BAR to C. You want to know whether it is differentiable, right? But if you look at the first, the motivating thing where I used exponential series, etc., okay, then what do you have? F of z is summation Cn z minus a to the power n 0 to infinity. Okay, and what we did was we formally differentiated it term by term. That is, we looked at the series. This is fn of z, and fn dash of z is what? N into z minus a to the power n minus 1. Therefore, I will have another series Cn z minus a to the power n minus 1. Okay. Here again, if you want, you can write n equal to 1 to infinity, because the first term is z0, that will be killed when I differentiate. Right? N equal to 0, this is f0, that will be 0. Okay? Right. Now, what I want to show is this series is convergent. Notice that this is again a power series. I want to show this is convergent. Okay? And once this is convergent, okay, and then next thing I want to show is this defines a function g. Okay, suppose it's convergent, it's a power series, it is convergent on BAR, and therefore call it sum as gz, therefore g will be continuous by whatever you have seen, right? Whenever the power series converges in a disk of convergence, okay, the sum defines a function which is continuous. Okay, this is continuous. What we are going to show is f dash z equal to g of z. In other words, if f of z is given by this power series, you differentiate it term wise, do the way we did, then you get, that's a derivative. That's it. It's like differentiating a polynomial function. It's exactly the same way. If you remember, this is how we motivated the exponential series definition and the power series in general. Okay, we have to prove that. Okay, let us go slow. So I want to know whether this series n times Cn and z minus a to the power n minus 1 is it convergent? Right? Right. Now what do I know where z is in BAR? Right? Okay. Now let's look at this. What I know is summation Cn z minus a to the power n is convergent. This is all I know. Right? Okay. So it's exactly like the same way I did earlier. Okay, I'm going to do a tricky thing. Okay, yeah. So let us look at z. Let us look at z naught. So that z naught minus a, z minus a is less than capital R. Yeah, right. Is that all right? Okay. So now notice that the series Cn z naught minus a to the power n, this is also convergent because mod z naught minus a is less than R, right? So I want to do exactly similar trick we did. So n times Cn z minus a to the power n, right? Let us look at z naught minus a to the power n into z naught minus a to the power n. Okay, this series equal to this series. Yeah, but what we know, again, if I look at rho as mod z minus a by mod z naught minus a, this is less than 1 because of this relation. Yeah, right? Okay. So what do I do now? So what I do is, let's look at if this rho, therefore this fellow, let's look at n times mod z minus a to the power n by mod z naught minus a. Let us look at mod to the whole power n, that is n mod z minus a by z naught minus a to the power n, and this is n times rho power n. Right? If you had followed my lectures on real analysis, especially in sequences, we have proved the following result. What is the result I proved? The result I proved was if rho is less than 1, a positive number, then n times rho power n goes to 0. Okay, recall. This is one of the basic limits which I said will be used in analysis often. Okay, many times students don't learn such things. Please go to that. Okay, I have done that. Okay, now let us look at this. So what do I have is, so now let's look at it. So this one, let's look at this absolute thing. So I have mod n, which is n mod Cn mod z minus a by z naught minus a to the power o n minus 1. Did I write n? Yeah, sorry, it must be z. Yeah, n minus 1. I'm sorry, I did a mistake. Okay, yeah. Okay, right. Into mod z naught minus a to the power n. I can take 1 minus r naught z naught minus a also. Yeah, this will be n minus 1. Is it okay? Right. Now what do I know? Yeah, so I know this goes to 0. Right? This is n minus 1. So this goes to 0. Right? Therefore, sorry, n times. I still have to get used to it. Please bear with me. I know mod n mod z minus a by z naught minus a to the power n. Okay, It goes to 0, therefore it should be less than mod z minus a. See, remember we are fixing z. We are fixing z in VAR. Okay, and we are doing this. Therefore, these are all fixed numbers. Z is fixed, A is fixed, Z not is fixed. Okay, this is less than. Okay, so this is a fixed number. Okay, so it has to go to 0. Therefore, given any positive number, if an goes to 0, that means mod an goes to 0. Therefore, if you give me any epsilon positive, then mod an should be less than epsilon for all n greater than or equal to capital N. Do you understand that? Yeah. Okay. So what I have shown now? So we have shown that summation, okay, n cn z minus a to the power n minus 1 in modulus is less than or equal to this object. That is going to be less than or equal to summation mod cn n times mod z to the power n minus 1 is less than or equal to mod z minus a, and that multiplied by mod z naught minus n to the power n plus 1. Let us make it z naught minus a. See, now you can see I am thinking, I am not, see what I am doing. So this is, I will write it mod z naught minus a. Okay, therefore this here, this will be mod n times this object will be less than or equal to this. Okay, therefore it is going to be mod zn less than or equal to mod z minus a, z naught minus a into mod z naught minus a to the power n minus 1, which is equal to mod cn mod z naught minus a to the power n. I'm sorry for the thing, don't get confused. There is n minus 1, that's it. Okay, yeah. So do you follow that? Okay. Now what do I know? Z naught belongs to BAR, and therefore I know this series z naught minus a to the power n is absolutely and absolutely convergent. Therefore this is convergent. Therefore I have shown this term-wise differentiated series is absolutely convergent. For every z in VAR. Right? You understood? Yeah. So the radius of convergence of this series is greater than or equal to capital R. Yeah. Therefore this, if I define g of z to be n times cn z minus a to the power n minus 1 infinity, this is continuous. Remember, whenever a power series converges in VAR, then it is going to be continuous on the sum function is going to be continuous. Therefore, this is continuous. Is that okay? Very good. What is the next one? Next one is, let's look at the power series f z. What do I know is this is f1 of z. What is f1 of z? f1 of z is cn z minus a to the power n. And what is f1 dash of z? That is n times cn z minus a to the power n minus 1. Right? Okay. Yeah. Now what do I know? Let us look at my partial sums. Sn. Okay, this is for f. Sn of z is summation 1 to n fk of z, which is summation ck z minus a to the power k equal to 0 to n. Sorry, 0. And what is Sn dash of z? That is nothing other than k times ck times z minus a to the power k minus 1. K equal to 1 to n now, right? But notice that this is nothing other than the nth partial sum of this series. Do you follow that? Now what do I know? I know that Sn converges uniformly to F and Sn dash converges to G uniformly on VAR, right? Now we had already learned from the uniform convergence a theorem. What is the theorem? Let me just recall. If you have on sequence of functions which converge uniformly on some disk and F1 dash converges uniformly on the same disk, then we know that F is differentiable and F dash equal to G. Yeah, therefore what do you think I have proved? I have proved that this series Cn z minus a to the power n 0 to infinity of z. So this is uniformly convergent and its derivative is n Cn z minus a to the power n minus 1 to infinity. Pause. Proceed. In the next video, I will also show a different proof. I will not make use of a theorem from uniform convergence, because the theorem which I quoted is usually proved in real analysis, and in real analysis you would have used the mean value theorem in the standard proofs you may see. So whereas I want to make use of the theorem even in the complex domain for z in complex numbers. So if you are very keen, astute reader, student, you will wonder, is that correct statement? So I'll give you a direct proof for that also in the next lecture. And I know this is demanding, but please go through it. You'll like it. And notice that we proved the power series when the term-wise differentiated series is also convergent, and at least the disk of convergence is the same as, it's not same, it's actually same, but we will not prove it at present. It converges on the original disk of convergence. Now I got F dash, which is G. Now it's again a power series which is convergent on BAR. Therefore I can again differentiate. So if I keep doing, you will see that the power series actually define an infinitely differentiable function. Please go through it, appreciate, we'll come back to it later.